Hello, welcome to this video. In this video, let us compare Otto, diesel and dual cycle for same peak pressure, peak temperature and heat rejection. We will compare it by using both PV as well as TS diagram. Now, let us start from PV diagram. Let us start with Otto cycle. Now, we know that Otto cycle is having reversible adiabatic compression 1 to 2, then constant volume heat addition, 2 to 3. Okay. This is our reversible adiabatic compression, then this is our constant volume heat addition. Then let us go for reversible adiabatic expansion. Okay. Reversible adiabatic expansion. So, this PV power gamma is equal to constant. Then this is our 4 to 1 is a constant volume heat rejection. This is our Otto cycle, all right. So, let us write it. This is again constant volume. 1, 2, 3, 4, 1 is Otto cycle, all right. Now, let us denote the same in TS diagram as well. Now, in TS diagram, this Otto cycle looks like first is reversible adiabatic compression. So, 1 to 2 is this, then 2 to 3 is constant volume heat addition, then 3 to 4 again reversible adiabatic, which is isentropic, all right. So, entropy constant or reversible adiabatic, both are same. So, 3 to 4 is isentropic expansion, 3 to 4 is isentropic expansion. Then 4 to 1 again it is constant volume, heat rejection. Okay. This is our Otto cycle in TS diagram. Now, let us take dual cycle. Now, what is dual cycle? Dual cycle is partial heat addition happens in constant volume and partial heat addition happens in constant pressure. And remember, we should do it in such a way that this peak pressure and peak temperature is same for same peak pressure and peak temperature. Now, in order to make the same peak pressure, we must extend this line. Okay. Then we will have constant volume partially. So, constant volume partially, then we will have heat addition constant pressure partially. Okay. So, now this cycle new cycle which we are writing is 1, 2 dash, 3 dash. Okay. This is our constant volume again, this is our constant pressure. Now, if you look at this cycle 1, 2 dash, 3 dash, 3, 4, 1 is dual cycle. Okay. If you look at 1, 2 dash, 3 dash, 3, 4, 1 is a dual cycle. Constant heat addition is happening partially at constant volume and partially at constant pressure. Now, let us write the same thing here as well in TS diagram. Now, this has to be extended a bit, that is 1 to 2 has to go little beyond this, so that we will have 2 dash. So, 1 to 2 dash is our PV power gamma is equal to constant. Then constant volume goes in parallel to this line for some distance. So, this is our 3 dash. Then we will have to go for constant pressure. Now, this is again constant volume. Okay. Now, this has to be constant pressure. Now, this will be much steeper, and we must know that peak temperature has to be same. So, peak temperature has to be same. So, this will be like, now we have maintained peak pressure same. So, dual cycle is 1, 2 dash, 3 dash, 3, 4 and 1. Okay. Now, let us go for, of course, we are maintaining same heat rejection. If you look at the curve 4 to 1, it is same for both the cycles, right. So, heat rejection we are maintaining same, that can be seen in TS diagram 4 to 1 is same, and peak pressure can be seen in PV diagram. So, highest pressure, that is P3 is same, that is the highest pressure for Otto as well as dual cycle, and similarly highest temperature, peak temperature is same for both dual as well as Otto cycle in this diagram. So, that we have maintained. Now, let us go for writing on the same PV diagram. Let us go for diesel cycle. Now, what is a diesel cycle? Heat addition happens at constant pressure, and that pressure has to be equal to this pressure. So, remember, so that pressure has to be equal to this highest pressure. Okay. So, therefore, we must extend this compression such that the highest pressure is same as that of the peak pressure which we have got in Otto as well as dual cycle. Okay. So, I shall write here same peak pressure. So, I have to extend this reversible adiabatic compression. Now, I will call this as 1, this as 2 double dash. Okay. Now, our new cycle is that is, if you look at the cycle separately, like 1, 2 double dash, 3, 4, 1 is our diesel cycle. Heat addition is happening at constant pressure. You see, 2 double dash 3 is a constant pressure heat addition process, and 1 to 2 double dash is reversible adiabatic compression. So, if you look each cycle separately, you can see that there is an Otto cycle 1, 2, 3, 4, 1. There is a dual cycle 1, 2 dash, 3 dash, 3, 4, 1. And if you look this separately, 1, 2 double dash, 3, 4, 1 is a diesel cycle. Now, let us write the same here in our TS plot. What we should do? We should extend this compression a bit more, and we should come back to the same peak temperature. So, this is our 2 double dash, 2 double dash. Now, this has to be in parallel to constant pressure, and the highest temperature or peak temperature must be same. Okay. So, this is our constant pressure again. So, therefore, now our diesel cycle is also complete. Now, let us compare this. Now, what do we know? We know this curve. Let us take the heat supplied or heat rejection area here, so that we can easily compare. We can compare the area and try to conclude. Now, call this as 5 and 6, let us say. So, this as our 5 and 6. Now, area under the curve in a TS diagram represents heat transfer, right. Now, what do we know? Efficiency equation will start with. Now, efficiency is given by W, that is work net divided by heat supplied. Work can be heat supplied minus heat rejection by heat supplied, or we can write that 1 minus QR by QS. And remember, we have kept the heat rejection same. What is the heat rejection? This area is heat rejection 4 to 1, all right. I mean 5, 1, 4, 6, the area in that zone is heat rejection, and you can see that for all the cycles, Otto, diesel and dual cycle, heat rejection is also kept same, as well as peak temperature and peak pressure. Now, that means QR is same. So, we will not worry about QR while comparing this efficiency of Otto, diesel and dual. All we will have to worry about QS. Now, you see, if we look at this expression 1 minus QR by QS, we must know that this must be less. That is, if there is 1 minus 0.1, the efficiency will be 90%. This we have discussed. If there is 1 minus 0.2, efficiency will be 80%. So, that means the second term has to be lesser in order to get higher efficiency. So, in order to get higher efficiency, second term has to be lesser. So, there is two options in order to increase the efficiency. One is we must reduce QR. So, for higher efficiency QR should be less or QS should be greater. Okay. So, we can directly say that those cycle which has higher QS, because QR is same, all right. So, for same QR, efficiency is directly proportional to QS, heat supplied. So, if QS is higher, efficiency will be higher. Now, let us see which one has the higher QS. Now, how can we do that? We can see that this is the area, total area, which is representing QS of what is this 1 2 double dash, that is diesel. So, diesel cycle has highest heat supplied, because area under this 2 double dash 3, or we can say area 5 2 double dash 3 5 2 double dash 3 6 5 is greater than area 5 2 dash, we can say this also 3 dash 3 6 5, and this is greater than area 5 2 3 6 5. Now, these areas are indication of what? Heat supplied. So, heat supplied, we are indirectly saying that heat supplied in diesel is greater than heat supplied in dual cycle. Okay. This is greater than heat supplied in Otto cycle. And we have already said the one which has got a higher heat supplied for same heat rejection and same peak pressure and peak temperature, we can say that efficiency is directly proportional to heat supplied. Therefore, we have proved that efficiency of diesel is greater than efficiency of dual cycle, and that will be greater than efficiency of Otto cycle. Okay. Thank you.